Okay, so I know that this question 1 was asked about on this worksheet, so I'll go over that one. So for these navigation problems with the airplane and the wind, it's always going to be where like the V that actually happens, which we call the V ground, because that's what you would see the airplane doing. What the plane is actually doing is the velocity of the plane plus the velocity of the wind. So that's kind of the key to understanding how that works. And it makes sense. Like if a plane wanted to go here, but the wind was blowing, let's say that way, well, the plane can't just go that way, otherwise it'll end up over here. So it's going to have to go this way to get there. So it's V plane plus V wind to get to the actual destination it wants to go to. So a plane is trying to fly, so that's its ground, 500 miles per hour in a direction of 150 degrees. So this is the same thing as 30 degrees north of west. And at the same time, there is a wind blowing at 50 miles per hour, 300 degrees. So that's going to be 60 degrees south of east. So this is our V ground. This is our V wind. So to find the V plane, we're just going to rearrange this equation to be V plane equals V ground minus V wind. So how do I draw that? Let's go 30 degrees. Actually, I'm going to draw that a little bit smaller. So it's going to be 30 degrees north of west. So that's 150 degrees. And this is 500 miles per hour. Maybe I'll have to draw that a little bit bigger. Crap. There we go. And then we're adding the negative VW. So where the wind was south of east, if you flip that to be the negative, then it becomes north of west. So now we're going 60 degrees north of west. So that's going to be something like that. And this is 50. I'll do it on the other side. 50. And this is 60 degrees right here. And so the velocity of the plane is going to be that right there, VP. And so then if this is 30 degrees, this is 30 degrees, this is 120 degrees, and so this interior angle is 150 degrees. So then you just do cosine law, 500 squared plus 50 squared minus 2 times 50 times 500 times cos 150. Square root that, you get 544. 544 miles per hour. Let's make sure that's right. Oh my, okay. Magnitude of resultant. Why am I getting a different answer? What? 300 degrees, so it's blowing that way. Yeah, this should, I don't know why the answer, what does the answer say? Wind. Oh. Oh, they're breaking into components. Okay, but that still doesn't make sense. 500 cos 30 is 433. 25. The answer key is not right because they're adding. Wait. Oh, I see. Okay, I read this wrong. They're saying that this is the velocity of the plane, not the velocity of the ground. So it's headed in that direction, and then the wind is blowing it to a different path. Oh, I didn't even read the whole thing. What is the magnitude direction of the plane's actual path? Man. Okay, so that changes it a little bit. So then we're going to go, now we're just dealing with the circled formula up there. So now it's just going to be, come on. Oh, that's not a straight line. 500, and then 60 degrees south of east, so that's 50, and that's, so this is 30. Pretend that was a straight line. So this line right here, how do I do this? This line right here is 30 degrees because that's parallel with that line. And then this is 60 degrees, which makes this 30 degrees. And so now we can just use 30 instead of 150. 500 squared plus 50 squared minus 2 times 50 times 500 times cos 30 equals, whoops, oh, no. Okay, so now I have 457, which is the right answer. 457. And then I would need to find this angle right here and then subtract it from 30 to get this angle right here. So that's just sine law. Yeah. I'm not going to do that. Does that answer the question? Does that make sense? I guess lesson learned, you should probably read the entire question before you start answering it. Okay, I need to insert the worksheet package for that part. Any questions so far? Anybody want to go over any other vector stuff? No. Okay, I believe I was asked to go over, what was it? Okay, let me see the chat here. First equilibrium problem. Yeah, we can do that. Okay, give me 1 sec. Okay, so the first question, the things in brackets are the answers. So you have to do it first. So weight 1, weight 2, weight 3 are the 3 weights suspended by the pulleys. Weight 3 is 12 newtons. What are the values of weight 1? Okay, so because of the nature of the pulleys, if you kind of track the forces here, let me just go back to this. Okay, good. The weight of weight 1, so this is going to be weight 1 or FG1 if you want. Like weight's the same thing as FG in this case, so it doesn't really matter. And then if it's not moving, then the tension that's going up is equal to weight 1. Well, the rule with tension, and hopefully you learned this last year or in physics 11, is that tension is equal throughout a rope. So this rope from this point to this point is going to be equal throughout. And so the tension that's pulling up this way, we'll call it tension 1, is going to equal the weight of the first block. Okay, because the weight is causing the tension, and so that tension is going to be pulling down on it. So instead of calling this T1, we're just going to call this weight 1. And the same thing for this one. This one's going to be weight 2. And then this one's weight 3. And so now we have our 3 vectors. So you can just go weight 2 plus weight 1 equals weight 3. Or plus weight 3 equals 0, I guess. and then plug in your values. So this is going to be 50 degrees right here, which makes this interior 50 degrees, and also this 40 degrees. And then this is 24 degrees. So this is all 74 degrees, which makes it 80 minus 74 minus 40. That one's 66 degrees. 66 degrees. And so from there, we can go sine 74 over weight 3, which is 12, equals sine 40 over weight 1. I did this upside down. I don't know why. Okay, let me do this the right way. The unknown should always be on top. So 12 over sine 74 equals weight 1 over sine 40. That'll be easier. Okay, so then it's 12 sine 40 divided by sine 74 equals 8.02. So weight 1 is 8.0 newtons. Okay, and that's right there. And then you just do a sine law again for weight 2. Okay, any questions about that?
Mr. Joe,
Yeah.
how did you get the 40 angle?
The 40, so because weight 3 is going directly down, straight down, that means I know that this is a y-axis. And so if this is 50 degrees, then this has to be 40.
Thanks.
Yeah. Any other questions? Anybody want to go over number 2? No? Good. I'm hoping everyone knows how to do FG parallel. Okay, making that assumption a little bit. Okay, number 2 would be great. Perfect. Okay, so number 2, an object is suspended on a frictionless inclined plane by a rope parallel to the incline. If the angle of the incline is 25 degrees, tension of the rope is 5,000. What is the weight of the object? So what we have here is 5,000 newtons. Technically, so FG is going down. So I'm drawing all the real forces acting on this thing. FG is going down, Fn, goes that way. And so if you add all those forces together, they're going to be equal 0. So then we're going to go Fn plus the tension of the rope. So this is Fn tension and then Fg like that. And then because this is 25 degrees, this right here is 25 degrees. And then what would that be? Fg is going straight down. Okay, so I'm gonna make this a little bit bigger. So that's your Fg going straight down. Now, if you remember from breaking down inclined planes, if you break Fg into components, you have Fg parallel. I might actually change the way I'm doing this because it's going to be easier. So Fg perpendicular and Fg parallel. Okay. And this was 25 degrees. I'm just having trouble visualizing this, and there's a way easier way to do it. Okay, I'm gonna do it the easier way. Okay, forget the triangle. Who has not seen this before? And it's okay, like just say, yeah, I have no idea what that is. Okay, so everyone's seen it. So I'm not going to break it down, but Fg, the way the triangle works out, if you break Fg into components, Fg perpendicular becomes mg cos theta, and Fg parallel becomes mg sine theta. And mg is the weight that you're trying to find. And so if I do it that way, I know that 5,000 is going up and Fg parallel is pulling it down. And so I can just say mg sine theta equals 5,000 in this case. And so the weight is what I'm trying to find. So mg sine 25 equals 5,000. So 5,000 divided by sine 25, which is 11,831 newtons, or this in scientific notation. Oh, some people haven't seen that. Okay, let me go over it for a sec. Let me do it over here. So if you have, when you have an inclined plane, here's the angle that it's inclined, and you have an object that's on the incline. Okay. FG will always go straight down. Okay, because it's gravity pulling it down. The normal force, normal means perpendicular. And so if you have an object on a straight like table or something like that, FG goes down, FN goes up because it's perpendicular to that surface. It's pushing straight up because the surface is level. If the surface isn't level, FN goes this way. Okay, it's perpendicular to the surface, where this is a right angle to the incline itself. So that part, you have to imagine that if you put a block on a ramp like this, it's going to start accelerating downwards, assuming that that force is bigger than friction and the incline is enough. Okay, it's going to start accelerating downwards. Now it's gravity that pulls it down, but it's not going to be all of gravity. It's not going to accelerate at 9.8 as if you were to drop something straight down. Okay, it's going to be a part of gravity. And so to figure out that part of gravity, what we do is we break FG into components. And so we do that by drawing two lines. Okay, one that's parallel to the plane itself, so we call it FG parallel, and one that is perpendicular to the incline, so we call it FG perpendicular. Okay, I'm going to move this a sec. FG parallel. Okay, now if you imagine this angle right here being formed between those two lines, this line right here is parallel to this line right here, which means that this angle right here is theta. Okay, now if that's theta and FG is going straight down, then this angle right here is 90 minus theta. Because this is parallel perpendicular, that's a right angle. And if you use the rule where it's 180 degrees in the triangle, this angle has to be theta. Okay, because this angle up here plus this angle down here has to equal 90. So 90 or theta plus 90 minus theta has to equal 90. So theta, it's just going to be theta. And so if FG is mg, then if you solve your sine and your cos, so sine theta will be FG parallel opposite over hypotenuse mg, then FG parallel will equal mg sine theta. Let me go back to this. Okay, and then if that's true, then FG perpendicular is mg cos theta. Okay, and so we'll get back to that when we get to circular motion. But also another thing about inclined planes, if there was friction, it'd be going up the ramp because the block wants to go down the ramp. And remember how friction is mu Fn. Oh, I need to post the formula sheet. Remind me to post the formula sheet. You won't need it yet. Okay, I'll try to remember that. Okay, so FF is always mu Fn. So if you have an object that you're pushing on a level surface, let's say we're pushing it this way with an FA, and there's FF going that way, then FF would equal mu Fn. But in this case, your FG and your Fn are the same thing. Okay, so we always change this to mu mg. Well, in this case, Fn is not mg. Fn is this guy right here, the FG perpendicular. And so the friction that's acting on an object on an incline is mu mg cos theta. Okay, so that's kind of a breakdown of inclines for those of you who haven't done it before. Okay. Let me check the chat for a sec. Okay, I think we're good. Any other last questions before we start the actual lesson?
So how to find the data? Like how what's the number of the data?
Theta is the incline. So this is 25 degrees right here. So that makes
Yeah.
theta 25.
Oh, okay. All right. Thanks.
Yeah. So whatever, like I'm labeling this as theta and this is theta. So whatever the incline is, that's the angle you're using in these formulas.
Thank you.
Yeah. Okay. Notes package. Let's talk about torque. Okay, so there's two types of equilibrium. There is translational equilibrium, which is the sum of the forces is equal to 0, and there's translation or rotational equilibrium. So rotational equilibrium occurs when there are two equal and opposite forces. The net force is still 0, acting on different points on an object. Okay, so if like a teeter-totter is an example. Okay, if you have a force pushing up on one side and down on the other side, it's going to start rotating. Okay, and in this case, my computer's not responding. There we go. In this case, this object, this bar here, will rotate this way, and that we call that clockwise. Okay, and the other way would be counterclockwise. Okay. Now, when a force, and this point right here is called the pivot point. Okay, the pivot or the axis of rotation. When a force acts away from the pivot, it's going to cause rotation. Okay, you do this every day when you open a door. You're applying a force at the end of the door away from the hinge of the door, which causes it to rotate around its hinge. Okay, you're using torque every day. Okay, so let's talk about torque. Again, my computer's not responding. Okay, here we go. Come on. Okay, torque is the tendency of a force to rotate an object about an axis, fulcrum or pivot, same name for the same thing, or different names for the same thing. So just as a force is a push or a pull, a torque can be thought of as a twist to an object. I usually do this demonstration where I have a student try to actually open a door by pushing on its hinges, and it doesn't work because you have to apply the force away from the hinge. So if this is like the top of the door and this is the hinge right here, if you push right here, nothing's going to happen. Okay, because you're pushing on the hinge. Your force is at the pivot point. But if your force is away from the pivot point, you're going to cause torque. So torque is force times distance. Okay, if a force is exerted at a distance from the pivot, the product of the force perpendicular to the lever arm and the distance to the force is the torque. Oh, I'm not going to do that yet. We're going to skip that part. Force times distance. So like if I were to have this, like this is the pivot point right here, or the fulcrum or whatever you want to call it. The force that's being applied, in this case, it's perpendicular to the lever arm, so the thing that's rotating, and the distance would be that right there, the distance from the pivot to the actual force that's causing the rotation. Okay, we're going to skip that because that's tomorrow's. General formula is blah, blah, blah. Torque is, okay, so torque is a vector quantity. However, now instead of using up, down, right, left, we're using clockwise or counterclockwise. And the units are Newton meters, okay, because torque is equal to F times D, which is newtons times meters. And so the condition of translational equilibrium, just like, so we have translational is the sum of the forces has to equal 0. For rotational, the sum of the torques has to equal 0. And torque is like the Greek letter tau or whatever. I don't know what Greek letter that is. And so what that means, if the sum of the torques is 0, so like if you break the forces into x and y's, some of the x forces is 0, some of the y forces is 0. But if you apply the vectors to torque, then torque, torque clockwise has to equal torque counterclockwise, okay, in order for them to equal 0. So this is the big relationship that we use in this unit, where our torques are equal in both directions. So there's some examples that are pretty basic where you're just plugging into a formula. So a torque of 24 Newton meters is needed to tighten a nut. If a person applies a force of 100 newtons, what is the minimum length of the wrench required? Okay, so all we have to do is go torque equals F times D. We need 24 Newton meters, and we can apply 100 newtons. And so the distance is going to be 0.24 meters. So the wrench has to be at least 24 centimeters. Okay. And obviously, if you had a wrench that's longer and you applied 100 newtons at, like, let's say 40 centimeters or 0.4 meters, then that would be a torque of 40 Newton meters. Okay, so it's, yeah, that's, but that would be more than enough. So, yeah. Okay, I said that already. Okay, center of gravity. So here's a few things that we need to know. If you were to hold up a meter stick, okay, let's say this is a meter stick, and put your finger right here, the meter stick would fall. It would fall this way, okay, around your finger. Same thing if you put your finger right here, it would fall again. If you put your finger right here in the middle, okay, assuming that it's a good meter stick and that it's level and all that stuff, the meter stick would balance. It would stay where it is. It would not rotate at all. Okay, so what that means is if you put your finger here and it rotates around your finger, there must be a force pulling it down that causes that rotation. Okay, but that force doesn't cause rotation when your finger is at that point. And so this point right here is the pivot point. Okay, well, technically it's not, but this is, we call this the center of gravity. Center of gravity. Okay, and that's where gravity pulls down. Okay, that's where gravity acts on an object. Now, this is important because if I have a wall and I want to hang a shelf on it, okay, I know that nothing's like this shelf is going to rip out of the wall, okay, because the center of gravity is right in the middle. And so it's going to pull down and cause rotation. What I need is something like a bracket to support it so that I have an upward force that is counteracting my gravity. Okay, so what you have to understand is there's two important parts. There's the center of gravity is where gravity is pulling. It's where the force of gravity acts on an object. And the second is that in a uniform beam, the center of gravity is in the exact center of that beam. Okay, which is why, like, you can't actually use a meter stick for this because meter sticks are not uniform. The mass of the wood in a meter stick is not evenly distributed, so it could be heavier on one side than the other. And so often when I try this in class, I have to put my finger at like 51 centimeters rather than 50 centimeters to balance it. So yeah, those are the two important parts. Point of rotation. Most problems will have an obvious point of rotation, so a hinge or a fulcrum, or it'll say this is where it's rotating, but it doesn't have to. You can put your point of rotation wherever you want, okay? So an example of this is, let's say I have a beam. That's a great beam. And I put a leg on that beam right here and another leg on that beam right here, okay? Well, there's technically three forces acting on this beam. And let's say it's a uniform beam so that the center of gravity is in the middle, okay? I have the center of gravity in the middle, so FG is pulling down. And then this beam right here is supplying a normal force right there. Okay, and this beam right here is supplying a normal force as well right there. Okay, how do I know that? Because if I make this my pivot point right here, this force right here is going to cause a torque counterclockwise, which means I have to have a force that's causing a clockwise torque counteracting it if that beam's not moving. And so this force right here causes a clockwise torque. Okay, however, it's going to erase the thing. If I erase this one and say this is now my pivot point, this force of gravity is now going to cause a clockwise torque, which means that I need a force that's going to cause a counterclockwise torque. And that's how I know that my FNs are both going up. Okay, because you can change where the pivot point is. I could even put the pivot point in the middle if I wanted to. Okay, so where your pivot point is up to you. Now, generally you want to put it in a place where you don't know what the forces are, because then those forces won't cause torque anyways, because any force acting on a pivot point doesn't cause torque. Okay, good. I'm recording. So yeah, that's the important. Any questions so far? I feel like I'm talking a lot. Okay. The last thing is lever arm. So I know it says that it's the distance from the axis to the rotation, but I just say the lever arm is the thing that's rotating. That's the easier way to say it. Okay, so if you have like a beam that is attached to a hinge, the lever arm is this whole thing that is rotating. Okay, that's an easier way to understand it. Okay, so let's do an example. Okay, so let's do this one first. So a 350 Newton store sign hangs from a pole of negligible mass, which means that the pole has mass, but it's small enough that it won't actually affect any torque. The pole is attached to the wall by a hinge, so that means this is our point of rotation, okay, that hinge, and supported by a vertical rope. What is the tension of the rope? So this store sign is pulling down on the beam that way, okay, and the rope is pulling up that way. Okay, now the first thing you want to do is figure out what's what. So if this is our point of rotation right here, the force of gravity is acting away from that point, which means that it's going to cause torque. And then which way is it going to go? Well, if you didn't have the tension, if you block that out, this force of gravity would pull it downwards, which would rotate it clockwise. Okay, and if you only had the tension, this would cause it to rotate counterclockwise. Okay, so then I only have two forces acting here. So then I would go torque clockwise equals torque counterclockwise. Okay, because that's true. If I had a third force, like if I had a force right here that caused another clockwise torque, then it would be torque clockwise plus torque clockwise equals torque counterclockwise. Okay, so all you have to do is, like, it's super easy to set up. You just start listing all of your torques. In this case, we only have 1 and 1, so it's easier. And then I go into my individual formulas. So the torque formula is force times distance. So this one is going to be Fg times its distance, and this one's going to be tension times its distance. So the Fg, we already know that it's 350 newtons. So it's going to be 350 times its distance from the pivot point, so that's 1.3 meters, equals the torque counterclockwise, which is the tension, which is what we're trying to find, times its distance, which is 2 meters. And now we only have one unknown, which is the tension, which is what we're trying to find. So 350 times 1.3, 455 equals 2T divided by 2. Tension is 230 newtons. Okay, I'm rounding a little bit. Okay. Does that make sense? Any questions about that? Okay. Next question. What are the vertical and horizontal components of the supporting force provided by the hinge? So in this case, there is no, like, the Fx is 0. There are no x forces going, there's no forces going in the x direction, so we don't have to deal with that. Now, in order to be in equilibrium, so this star thing up here, an object that is in equilibrium must have both translational and rotational equilibrium. So the sum of the torques is 0. We already figured that out up here in part A, but the sum of the forces in the y direction also has to be 0. Okay, so now I can start listing all my forces, and it looks like I only have Fg and T, so I can start listing those. Fg is going down, tension is going up, plus some other force that's acting at the hinge has to equal 0. Okay, so I'm going to do it that way. Because I know that, like, my tension's 230 and my Fg is 350. Those two aren't equal, so there has to be another force somewhere. Okay, and I know that it's going to be going, well, I'll show you that in a sec. Okay, so negative 350, that's the Fg going down, plus the tension, which I just found to be 230, plus the force that's at the hinge is equal to 0. And so, whatever this is, the leftover, 120. So this is, like, this becomes negative 120 plus FH equals 0. So FH equals positive 120 newtons. Okay, now this positive means that it's going up. Okay, so I'm adding it here, but I'm not defining, like, it's like I'm adding the absolute value of FH. Okay, so if my answer comes out as negative, that means that it's going down. If my answer comes out as positive, that means it's going up. Okay, so there is a force acting on the hinge, but the reason why we don't include it in our torque is because the torque is F times D. If that D is 0, then the torque is 0. Okay. Okay, last question, I think. This isn't an angle one. So a uniform beam is pivoting on its center of gravity. So that means we have a beam like that, and in the middle, there's a pivot. 60 centimeters to the left, there's a 12 Newton hanging object. So that means something like, let's go right here, there's 12 Newtons, 60 centimeters away from that object. And then 80 centimeters to the right of the pivot, there's another hanging object. So we'll go right here, there's another hanging object, which we don't know, and that's 80 centimeters from there to there. What is the force of this other object if the beam is balanced? So if this is our point of rotation, this force right here causes a counterclockwise torque, and this force right here causes a clockwise torque. Okay, so in this case, we just need to go torque clockwise equals torque counterclockwise. F times 0.8 equals 12 times 0.6. Notice how I'm turning my centimeters into meters because it's Newton meters. 12 times 0.6 divided by 0.8. F is 25. That doesn't make sense. Give me a sec. 12 times 0.6. There we go. Divided by 0.8. 9.8 newtons. 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 Okay, now notice how the further away object, or the further away force, is less than the closer force, because the closer you are to the pivot, the more force is required to cause rotation, and the further away you are, the less force you need. And this is extremely practical. Okay, so I have a car and I had to change its tire, and so I have a tire and there's a lug nut, a thing of lug nuts on it. The jack, or the wrench that came in my car is tiny. Okay, and so I put it on my car and it's like that, and I can't get any rotation. So what I did is I bought a bar to put over it that extends it to there, and now it's really easy to loosen. Okay, because it requires way less force at this point than it does at this point to rotate. So if you're ever having trouble getting something off, just increase the distance you are away from that thing you're trying to rotate, and it's way easier to rotate. Okay, because you require way less force. So there you go, something practical that you can take away from physics, which I only ever use when I'm working on my car. So maybe if you're into cars, you'll use this. So that's all we're doing for today. You can see that there's only one example for tomorrow's lesson. So tomorrow's lesson will be fairly short. So don't worry about getting lots of work done today. You'll have lots of time tomorrow. Any questions?
I just was wondering, how do you know which one's counterclockwise and which one's clockwise? Do you just look what way the beam would go?
Yeah, exactly. So like what I do is you look at the individual force. So forget, like if I'm looking at this force right here, forget this force exists. If this is your pivot point, so you're holding it here and you're pulling down here, it's going to cause this whole thing to rotate this way, which is clockwise.
Okay, thank you.
Okay. And the same way, if you have a beam like this and you're pulling down on this side, it's going to cause rotation to go that way, which is counterclockwise. So yeah, you're looking at the individual force and where it is in relation to the pivot and where it is on the lever arm and which way it's going to pull the lever arm. Like in this case up here, if it's going to pull the lever arm up, that's counterclockwise. If it pulls it down, that's clockwise. Any other questions? No.
Wait, so one side is going up, is clockwise? You mean
Well, it
right
depends.
side?
It depends on how you draw it. Like if I do it like this and make my pivot point right here, then this is going to cause counterclockwise.
All right.
And this would cause clockwise. But if I change my pivot point to being right here, then up is now clockwise and down is now counterclockwise.
All right.
Okay, so it depends on where the force is in relation to the pivot.
All right. Thank you.
Yeah. Okay, if there's no other questions, then I will sign off for today, and we will continue tomorrow at. Let's have a sleep-in day. Let's start at, because it's a short lesson, so let's just go with that gives you more time to work tomorrow too. Let's go at 10 o'clock tomorrow morning. Does that sound good, everyone? It's a Friday, right? Tomorrow, Friday? Yeah, I think so. Okay, so let's go 10 o'clock tomorrow. Let you guys sleep in a little bit. Okay, that's it.
And can I ask you a equilibrium question?
Yes.
After this chat and.
Yep. Yeah, everyone can leave and then I'll just hang around.
Yep.
Okay. I'm going to stop recording and then stop sharing. I'll stop recording right now and then you guys can leave.